Welcome to This Explainer. Today, we're going to unpack a technology that feels like it belongs entirely in the future. Yet, it's actually been in development for decades. We're talking about magnetic levitation, or Maglev. It promises speeds that rival airplanes, but right down here on the ground. But here's the thing, the way it actually achieves this is wildly misunderstood. When most of us picture a maglev train, we immediately go straight to that ultimate sci-fi dream. We envision this serene, passive pod just gliding effortlessly and silently above a metal track. We kind of think of it as floating, right? Like a leaf gently resting on this invisible cushion of air. It's a beautiful, frictionless, and honestly incredibly peaceful mental image. Well, I hate to burst that bubble, but we need to shatter that illusion right away. What if I told you the train isn't peacefully flying at all? Actually, scratch that. It is continuously and violently fighting a mechanical battle just to keep from crashing into the track at hundreds of kilometers per hour. The reality of maglev is an intense, high-stakes game of physics. So, let's jump right into Section 1, the flying train illusion. To truly understand this engineering marvel, we kind of have to look past the vehicle itself. The true protagonist of the story isn't the train, it's the guideway. The guideway is not just a piece of passive steel like a traditional train rail, it's a highly active, deeply complex structural mega machine. It totally replaces the traditional rails and contains all the active or passive coils required for the whole shebang to work. The train is essentially just a shell. The track is doing the heavy lifting here. Which brings us to Section 2, the most expensive air gap. Okay, so the first major piece of tech we need to wrap our heads around is EMS, or electromagnetic suspension. EMS uses controlled active magnets to literally pull the train up towards the guideway. Systems like the German-designed Transrapid TR-07 don't push off the ground. Instead, their magnets are located on structures that wrap underneath the track, and they magnetically attract upward toward the steel stators on the guideway to lift the whole vehicle. And that brings us to an absolutely mind-blowing number, 8 millimeters. That is the clearance the Transrapid EMS system operates with. I mean, just think about that for a second. You have this massive passenger vehicle hurtling forward at 400 to 500 kilometers per hour, and it is hovering just 8 millimeters away from solid steel and concrete. This is for sure the most expensive air gap in the world. Because that gap is basically microscopic in heavy engineering terms, it has to be actively managed to prevent the train from touching the track or, on the flip side, just floating away. It doesn't just rest there passively. Onboard computers are monitoring that exact 8 millimeter gap an astonishing 10,000 times per second. They're constantly adjusting the magnetic force to avert disaster. And to make this safe, the system relies on independent, redundant gap sensors. So if one passes over a thermal expansion joint in the rail, another one instantly covers for it. It even has 4 completely autonomous 440-volt direct current onboard battery networks just to ensure the levitation never fails, even if the primary power is totally lost. If you look closely at this cross-sectional view, which is pulled straight out of the engineering safety reports, you can really see what I mean. Notice how the vehicle structurally wraps entirely around that T-shaped guideway. The levitation magnets are situated way down on those bottom arms, pulling upward against the underside of the T-shape. This brilliant illustration really proves just how radically different this is from a standard train simply resting its weight on a steel rail. Moving right along to Section 3, unrolling the electric motor. So, we've established exactly how we keep this thing suspended in midair. But how does a massive machine actually move forward at such terrifying speeds when it doesn't have any wheels driving it? The secret here is the linear induction motor, or LIM. I want you to imagine taking a standard spinning electric motor, like the kind you'd find inside a desk fan or an electric car. Now imagine taking a saw, slicing that motor open, and unrolling it perfectly flat along the ground. Instead of generating a rotational force, or torque, this unrolled motor produces a linear force directly along its entire length. And this brilliantly illustrates the whole paradigm shift of maglev. With a traditional rotary motor, the engine sits inside the vehicle, right? And it turns wheels to push against the ground to generate forward motion. But with a linear induction motor, the entire track is the engine. A traveling magnetic wave is generated in the guideway itself. By rapidly alternating magnetic poles, the track literally reaches out with invisible magnetic forces to pull the train from the front and push it from behind. It's incredible. All right, let's turn up the heat, or rather, the cold, in Section 4, superconducting at 500 kilometers per hour. Let's see how this all builds when we push the tech to its absolute physical limits, specifically looking at Japan's incredible SCM Maglev system. Now, while the German Transrapid uses EMS to pull the train up, the Japanese system uses EDS, or electrodynamic suspension. EDS uses powerful superconducting magnets to push the train away from the guideway via magnetic repulsion. The guideway has these really cool figure-8-shaped coils. As the train accelerates on rubber wheels, its magnetic fields induce a current in the track coils. And thanks to Lenz's law, this creates a reactive, opposing magnetic field that repels the train upward. Once it hits about 150 kilometers per hour, that magnetic repulsion gets strong enough to lift the whole train a full 100 millimeters off the guideway. But here's the catch. To get magnetic fields strong enough to push a massive train at 500 to 600 kilometers per hour, your standard magnets just aren't going to cut it. The SC Maglev relies on niobium titanium superconducting coils, and to make them actually superconductive, they have to be cooled down to minus 269 degrees Celsius using liquid helium. Just think about the sheer engineering madness happening here. You've got a blazing fast passenger train traveling at half the speed of sound, and sitting right inside the bogies is an absolute zero cryogenic environment. Wow. And that leads us perfectly into our final segment, Section 5. The ultimate engineering nightmare. This brings us to a really harsh reality check. If this technology is so fast, so frictionless, and so incredibly advanced, why don't we see maglevs replacing traditional rail networks everywhere by now? Well, it all comes down to this staggering financial truth. Take a look at this breakdown drawn from engineering research on maglev girder bridges. Between 60 and 80% of the initial investment for a maglev project is swallowed up entirely by the guideway infrastructure alone. That incredible track that acts as both the engine and the levitation platform, it is just prohibitively expensive to build. There's a quote from the infrastructure studies that really hits the nail on the head. It says, "Under external forces, the allowable variations of such structural parts are extremely minimal." Basically, a maglev guideway isn't just a track. You have to think of it more like a high-speed concrete runway. When a massive vehicle passes over it at 500 kilometers per hour, it exerts these unbelievable magnetic and dynamic forces straight into the concrete. The guideway has to remain perfectly, completely rigid. Because remember, in an EMS system, we are literally fighting to maintain an exact 8-millimeter gap. The structural tolerances required to make this happen are just terrifying. You have these massive welded steel or concrete girders spanning 25 to 50 meters up in the air. The final fitting of these giant beams has to be performed on-site, using computer-aided precision measurements. Engineers have to carefully model surface roughness, dynamic displacement, and vibration just to ensure the track doesn't bend or warp even a tiny bit. As an infrastructure project, building hundreds of kilometers of this stuff is arguably the highest precision heavy construction job on the entire planet. Now, for the focused learners out there who really want to dig into the rigorous math and the logistics behind all this, here are some absolutely excellent resources. I'd highly recommend looking into the Japan Central Railways data on the SC Maglev, diving into IEEE's technical journals, exploring MIT's open courseware on electromechanical systems, or reading up on the operational costs over at the Railway Gazette. And that brings us to the end of our explainer. We've gone all the way from the illusion of a peacefully floating sci-fi pod right down to the intense reality of cryogenic magnets, unrolled electric induction motors, and a frantic computer system managing an 8-millimeter gap 10,000 times a second. So I want to leave you with this question to chew on. If the true marvel of maglev isn't a flying train at all, but is actually the most complex, demanding, and expensive concrete runway ever built, will this incredible technology ever truly replace the humble, low-maintenance steel rail? Something to think about. Thanks so much for joining me on this explainer, and keep questioning the technology around you. Catch you next time.